At nearly 170 miles per hour, aircraft tires have to absorb the impact of a plane weighing more than 500,000 pounds. Remarkably, they repeat this process dozens of times a day and almost never explode. Why is that? Let's explore what's really happening inside aircraft tires with Mido Explained. Let's begin. Few people realize that the story of airplane tires actually began with an airplane that had no tires at all. In 1903, the Wright brothers' Wright Flyer made the first powered flight in history, not from a runway, but from an 18-meter wooden rail track. No wheels, no tires, no landing gear. It moved like a sled and landed the same way. 6 years later, in 1909, Goodyear created the first pneumatic tire designed specifically for airplanes, replacing bicycle tires and skids used on early aircraft at the time. The material was simple: natural rubber reinforced with cotton fabric. Basic, primitive, and for many decades afterward, almost nobody questioned whether it was truly good enough. Then, July 25, 2000 happened. A Concorde operated by Air France was accelerating down the runway at Charles de Gaulle Airport for a flight to New York. 5 minutes earlier, a McDonnell Douglas DC-10 from another airline had accidentally dropped a small strip of titanium onto the runway, so small that nobody noticed it. The Concorde rolled over it, a tire burst, and pieces of rubber slammed into the fuel tank beneath the wing. Flames erupted, and the aircraft crashed less than 2 minutes later. A single tire failure led to the deaths of 113 people and helped bring the entire era of commercial supersonic travel to an end. Just 3 years after the disaster, the Concorde was officially retired and never flew again. From that moment on, the aviation industry began looking at airplane tires very differently. And what engineers built after that disaster is exactly what we are about to explore next. Looking from the outside, airplane tires do not seem that different from truck tires, just larger and thicker. But if you cut one open, the inside looks more like a multi-layer sandwich than a solid block of rubber. The outer layer is made from natural rubber, not synthetic rubber like ordinary car tires. The reason is very specific. Natural rubber handles heat far better, with a critical limit of around 390 degrees Fahrenheit before it begins to break down. That number matters because the surface temperature of an aircraft tire can spike close to that limit the instant it touches the runway. Beneath that rubber are multiple layers of woven nylon and aramid fibers. Aramid belongs to the same family of materials as Kevlar, the material used in bulletproof vests. Added to that is a reinforced steel and aluminum core inside the wheel assembly. Everything is compressed, vulcanized, and tested under enormous pressure. The result is a tire capable of supporting up to more than 83,000 pounds during testing. And before it is ever approved for service, it must survive a burst test, meaning engineers inflate it to nearly 800 psi before it finally fails, about 4 times higher than its normal operating pressure. In other words, aircraft engineers design airplane tires with a safety margin 4 times beyond their real-world operating limits. Not because they are overly cautious, but because in aviation, almost correct is not an acceptable answer. If you've ever wondered why airplane tires aren't inflated with regular air like bicycle tires, the short answer is because regular air can kill, not figuratively. At cruising altitude, the outside temperature of an airplane can drop to around -58 degrees Fahrenheit. Regular air contains moisture, and at that temperature, the moisture will freeze inside the tire, causing pressure to fluctuate in ways that are very difficult to control. But that's not the most dangerous part. When the plane lands and the pilot brakes sharply, the temperature of the braking system can skyrocket to hundreds of degrees Fahrenheit in just seconds. If the tire were filled with regular air, meaning it contained oxygen, then the tire would be in an extremely high-temperature environment surrounded by a combustion-enhancing substance. Just a small spark could turn the tire into a serious malfunction. Nitrogen is different. It's an inert gas, non-reactive, doesn't support combustion, and contains no moisture. Furthermore, because nitrogen molecules are larger than oxygen, they escape through the tire walls significantly more slowly. This helps maintain more stable pressure across a range of temperatures, from -58 degrees Fahrenheit in the sky to hundreds of degrees Fahrenheit during emergency braking on a runway. This is not an optional choice, but a mandatory regulation by the Federal Aviation Administration after at least 3 accidents involving tires catching fire due to the use of regular air. Airplane tires are not spinning before landing. There is no motor that spins them up beforehand, and no special preparation system at all. They are completely still. Then, the moment the wheels touch the runway at nearly 170 miles per hour, friction instantly drags them from 0 to that speed in less than half a second. That is exactly where the white smoke you see during landing comes from. It is not burning brakes, and it is not a malfunction. It is the surface rubber being burned away during that split second when the tire matches the speed of the runway. But the tires are not handling the impact alone. Inside the landing gear are hydraulic cylinders that work like giant shock absorbers, absorbing most of the landing force before it ever reaches the tires. The tires are only the final line of defense, but they are still one of the most important parts of the system. And those grooves running across the tire surface are not there for decoration either. Airplanes land on wet runways at around 170 miles per hour. And without water drainage grooves, even a thin layer of water would be enough to create hydroplaning, where the tires ride on top of the water instead of gripping the runway. At those speeds, the consequences do not need much explanation. Inside the wheel assembly, not on the tire itself but on the metal wheel rim, there are small components called fusible plugs. They look like ordinary bolts, but they are hollow inside and filled with a low melting point alloy, similar to the solder used in everyday electrical work. They are designed for a very specific situation: a plane accelerating down the runway, the pilots detecting a problem, and then performing a high-speed rejected takeoff with heavy emergency braking. That braking generates enormous heat, which travels into the wheel assembly. And once the temperature reaches a dangerous level, the alloy inside the fusible plug melts, allowing the tire to slowly and safely deflate. Instead of exploding and sending fragments flying everywhere, the tire loses pressure gradually, more like a balloon slowly leaking air. The aircraft stops more safely, ground crews nearby are protected, and most passengers never even realize anything happened. In a way, this is basically the fuse of an airplane tire, sacrificing itself to protect everything else. And that idea reflects the design philosophy behind the entire system. Not preventing failure completely, but making sure that if failure does happen, it happens in the least dangerous way possible. A commercial airplane tire usually lasts only around 200 to 300 landings before it needs to be retreaded. That may sound like a lot, but think about it. A commercial aircraft can fly 3 or 4 trips a day. In less than 3 months, the tire may already need servicing. But the tire is not thrown away after that. The outer rubber layer is shaved off and replaced while the internal structure is kept, almost like peeling the skin off a fruit and reusing the core inside. This process can be repeated around 7 to 10 times before the tire finally reaches the end of its life. And the financial cost is far from small. A single tire for an Airbus A380 costs around $5,500 and the full set of 22 tires on one A380 can cost more than $120,000 for a complete replacement. A Boeing 747, with its 18 tires, costs roughly $90,000 to $100,000 per full set. Replacing one tire on an Airbus A320 takes about 45 minutes with a full maintenance crew. Meanwhile, a NASCAR pit crew can replace 4 tires in under 3 seconds. But to be fair, they are playing very different games. And after all those retread cycles, airplane tires do not end up in landfills. Many are recycled into playground surfaces or tires for agricultural equipment. So in a strange way, farmers using tractors today are still benefiting from aviation technology, just in a very different form. Looking back at the entire story, from the Wright Flyer sliding along a wooden rail, to the Concorde being brought down by a tiny piece of metal on a runway, to modern aircraft tires filled with nitrogen and reinforced with aramid layers and fusible plugs, one thing becomes very clear. Nothing in an airplane tire is there by accident. Every material layer, every type of gas inside the tire, every small plug hidden inside the wheel assembly exists for a very specific reason. Usually because, somewhere in the past, someone did not have it and paid the price. So the next time you see that white smoke rising when a plane touches down on the runway, you already know what it is. It is not something to fear. It is decades of material engineering quietly doing exactly what it was designed to do, at precisely the right moment, without anyone even noticing.